This seminar is going to consist of essentially 4 sections. All right, we're going to have a group of speakers this morning, one this afternoon, one tomorrow morning, one tomorrow afternoon. The first group of speakers is going to be a group that I know fairly well. We're going to have Dr. Ali Sekmen, who is former department chair at the University of Tennessee Computer Science Department. He has a PhD in mathematics from Vanderbilt. He also has a PhD in electrical engineering from Vanderbilt because one just wasn't enough for him. We have Dr. Tim Wallace, who is a TSU graduate, and I'm going to go look at Tim's biography because I don't remember what I was going to talk about. Sorry. He is a professor of computer science and the chair of the biomedical data sciences department at Meharry. He is a fundamental researcher as well. He's not just an administrative guy. He does work in tensor decomposition, wavelet theory. I remember looking at wavelet theory back in my first undergraduate days and going, it hurts. So I'm glad to know somebody who works on it. And also presenting will be Dr. Badahir Bilgin, who is a research assistant at TSU currently. And you're getting your PhD from Middle Eastern Technological University, which is an extraordinarily good school in Turkey. All right, so without any further ado, here is Dr. Sekmen. Oh, you want the mic? All right.
Good morning, everyone. Good to see all of you, and I want to extend a warm welcome to both all the participants here in Nashville in person and also all of those who are joining us online. And I have the pre-workshop survey. I'm assuming that most of you have already done it. If you haven't, can you please go ahead and complete it? So Dr. Melton explained it very well, but I'm going to tell you the reasoning why we are here, okay? And first of all, how many of you have worked with deep learning so far? Anybody work with deep learning? Do we know what deep learning is? Okay, so I'm going to go a little more fundamental and explain why we are doing this mathematics of deep learning workshop. And of course, I need to explain what deep learning is, right? So first of all, okay, let's see. I'm going to make this one work. Here you go. Yeah. Well, all right. So as Dr. Melton mentioned, we have a grant from National Science Foundation. Of course, this is part of it, but the main motivation is not just this grant. We really want people, or especially the researchers at Tennessee State, Meharry, Fisk, Vanderbilt, and other institutions, and also globally, many participants to understand more mathematics of AI and ML. So what is AI? AI typically deals with, I've just prepared this slide for you, but when we say AI, you can consider that they are software systems that can handle the tasks that we normally think only human beings can handle. Like until recently, we used to think that driving a car is a human thing, right? Or this conversation that we are having together. For example, Dr. Melton explained things. Now you know Dr. Melton. And when you see her at lunch, you're going to probably say something about this morning, right? Because you learn. So people learn, so machine learn as well, right? So the focus of AI is how to make the things that we normally think only human beings do by machines. And there are different ways of implementing AI, and one way is machine learning. So machine learning is a sub-area of AI, okay? But this not the only sub-area of AI. We have other systems like expert systems, symbolic AI, robotics, fuzzy logic, genetic algorithms. These are other areas of AI as well. But machine learning is the main way that we implement AI systems. So AI is the big topic, and then we have machine learning as a sub-area of AI, okay? Under machine learning, of course, there are different ways to implement machine learning systems like support vector machines, regression, random forest, reinforcement learning, and things like that. But the main way that we implement machine learning systems is via deep learning, nothing but neural networks, okay? So we are going to focus here on neural networks. Have you heard about neural networks before? Okay, so how did it start? Actually, as an undergraduate student, when I did my senior project, I did work with neural networks, mid-90s. And it was, a lot of people started working there, but neural networks were computationally very heavy. So working on a neural network with, older CPUs, that was not practical. So for a while, people stopped working on neural networks, or at least advancing neural networks. But in 2012, there was a breakthrough, okay? A group introduced, actually CNNs, convolutional neural networks, is one of the neural network architectures that's not new, but it was not practical to implement until GPUs were available, more available. And GPUs are computational units similar to CPUs, but they are more suitable for machine learning implementations. I'm not going to get into GPUs, of course. But in 2012, until 2012, there was a competition called ImageNet competition. That's object recognition competition, okay? So until 2011, that was reasonable. But in 2012, a group who's using CNNs made a considerable improvement in that competition, okay? So 2012 is the year we also started working on CNNs. 2013, we started. So in that, after that, but CNNs are mainly for computer vision, like vision systems. If you want to develop a neural network or AI system that utilizes or uses computer vision, it may be optical, thermal, any kind of vision system, they typically use CNNs. So that was the first architecture. But then in 2017, Google introduced another architecture called transformers. That was another breakthrough, okay? So, and all ChatGPT is a large language model, right? So basically transformers are AI architectures that are mainly at that time used for text processing, natural language understanding and things like that. And then we started having large language models. For example, GPT-4, BERT, these are the models that are based on transformer architectures. And then we have ChatGPT and Copilot and things like that. We have the apps. So two main architectures. One is CNN, mainly for vision data, and then transformers, mainly for text. Transformers started mainly for text, but now it is for multimodal everywhere, okay? So that's why today we are going to focus on this workshop focuses on mathematical understanding of CNNs and transformers. Is that clear? And many people use AI, right? All of us use AI, but do we understand what is happening? And it's extremely simple. You will be so surprised how simple neural networks are. And our work at TSU is to understand why neural networks work the way they do. Understand more mathematics. As we understand more mathematics, we can contribute to it, right? We're not going to be competing with Google, Amazon. They're giant. But as academic institutions, we can always contribute in the algorithmic level, right? So that's the focus that we are going to have in these 2 days. As Chris already explained, but I want to extend a thank you to National Science Foundation, Tennessee State University, but not only Tennessee State University. We have speakers from Meharry, and we have Vanderbilt, and I know that we have participants from Fisk and all other institutions. So I like to thank all those institutions. Okay, so, and I'm going to start with linear algebra. Why linear algebra? First of all, we are going to approach this deep learning from matrix perspective. Okay, so we are going to understand the matrix operations and think about data. Let's think about like 200 by 200 image, 200 pixels width and 200 pixels height. So 200 times 200, is it 40,000? Is it? Okay, so that means the image is actually a 40,000 dimensional data point, okay? So one image lives in 40,000 dimension. Think about that you're doing a face recognition system and you collected 10,000 face images. And each image is 40,000 dimensional, right? And think about it as a vector. 40,000 dimensional vector, and since you have 10,000 of them, it becomes a matrix. You understand? And that matrix is 40,000 by 10,000. So that's your data. From this point on, you converted your data science problem into what? A matrix manipulation problem. But then you will say, hey, I don't want to work on 40,000 dimensional space. Nobody wants to work in 40,000 dimensional space. Is that right? So actually, you don't have to, because in real world problems, even though data comes from very high dimensional space, they live in a smaller or lower dimensional subspaces. So, but you don't know what a subspace is, right? You're going to learn today, this morning. So we are going to talk about what's a space, what's a vector space, what's a subspace, and instead of working 40,000 dimensional, how do I know to project to a lower dimensional space? First, if I'm going to project it, what should be the dimension of the lower dimensional space? What is a dimension anyway? So these are all the topics of this morning. Do you understand? And then Tim is going to talk about a very important matrix decomposition, singular value decomposition. That's like a magic tool. So, and then we are going to use singular value decomposition to project data in a lower dimensional space, which simply called principal component analysis. Maybe you heard about it, PCA. So this morning, you're going to understand the fundamentals of linear algebra. You're going to understand a space, a subspace, and then some matrix decomposition tools, singular value decomposition. And there's another one called CUR decomposition, which is singular skeleton decomposition. That is not known much, but it's very useful. And then I will also, after Tim, I'm going to show you how you can implement PCA with maybe 10 lines of code, and you will understand what it is. Are you guys with me? All right, so let's get started with linear algebra. I guess we need to do screen sharing again, Kemal. Okay. Yeah, here you go. Is it share? All right, so everybody can see it. All right, so I'm gonna go a little fast, but and also some of those will be trivial to you. So just bear with me. Okay, if it is trivial, don't assume that it's gonna be trivial all 2 days, especially tomorrow morning when we talk about CNN and also transformer architectures. It's gonna get complicated, but the fundamentals will be given today. In the morning, linear algebra, and then in the afternoon, we are gonna have matrix calculus. Okay. And I think you're going to enjoy. Again, give me 1 second. All right, sorry. Okay, now it works. All right, so again, a brief outline. We are going to talk about, first I'm going to talk about system of linear equations. And you may say, why? You will understand, okay? We'll talk about the system of linear equations. We're going to talk about what a vector space is, what a subspace is. We'll talk about linear independence. We'll talk about span and basis in 25 minutes, okay? So, all right, so system of linear equations. I'm going to talk about reduced rough echelon form, which is extremely simple concept, but extremely useful, okay? So when we have a set of linear equations, but of course, let me introduce what a matrix is, and if you are not familiar with, but matrix is nothing but a two-dimensional array, okay? So a matrix is a bunch of numbers. We have m rows and n columns, and this matrix is called m by n matrix, when you have m rows and n columns. Of course, the data doesn't have to be numbers, but in our case, they are going to be numbers. So that's what it is. It's a two-dimensional data structure or array. So think about two equations. We have 2x plus y is equal to 3. I don't know why PowerPoint is showing like this. Maybe I prepared it in Mac and this is Windows. So we have two equations. And how do you find the solution to those two equations? It's extremely simple, right? Basically, you have two lines. You have one line here, and you have second line, and the intersection is your solution. Everybody agrees on that? But what if I have like 20 equations? Are you going to have all the lines and things like that? That's not practical, right? So we are going to learn how to solve this problem by creating an augmented matrix and find the reduced echelon form of the matrix. Okay? Sorry about this. I'm not sure what's happening here, but basically get the coefficients 2, 1, 1, 1, and then get what you have in the other side of the equation, and we call it an augmented matrix, okay? And then start doing some row operations. So this is your augmented matrix, 2, 1, 3, 1, 1, 1. Everybody's okay with that? How I created the augmented matrix? It's very trivial, right? So basically coefficients and also the other side of the equation. So what you need to do is just do row operations. Think about this equation here. 2x plus y is equal to 3. What if I say 4x plus 2y is equal to 6? Are they the same equation? So multiplying by 2 doesn't make any change, right? Or dividing by 2 doesn't make any change, right? So that's exactly the idea. I'm going to start with this. I'm going to divide row 1 by 2. Nothing changes. Do you agree? And then I'm going to go and subtract. I'm going to go and subtract this second row from the first row. It's not going to change anything. The second equation subtracted from the first equation, but as long as you subtract the other side of equality sign, equal sign, then everything is the same. So you continue like that. You do, for example, multiply row 2 by 2. You continue like this. And finally, you convert your augmented matrix in a matrix who is the first side is an identity matrix. You see that? 1, 0, 0, 1. So do row operations, subtract from one row to another one, and so on. Do whatever you need to do. And finally, you convert this one to 1, 0, 0, 1. Once you're done, you're done. Once you did that, you're done. Then you say, this one, 1, 2, right? That means x is equal to 2. And then this guy, y is equal to 1, negative 1. So that's how you solve and find unique solution. Is that clear? Nothing complex. Just do reduced of echelon form and then look at the augmented matrix. Let's do more examples. And now let's do a little bit with 3 equations. So how do I find the solution to those 3 equations? Again, the same idea. I'm going to create reduced of echelon form of the augmented matrix. And in order to do augmented matrix, 2, 1, 3, these are the coefficients here, 1, 1, and 2, 0, 1, and then 5, 2, 3. Everybody's with me? Okay? You can stop me if you have any questions. Okay? And then just do simple row operations. Go. And finally, convert your matrix into this one. See, this is the identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. Once you convert it to that with simple row operations, all you need to do is look here. This is 1, this is 1. That means x is equal to 1. Y is equal to 0, and z is equal to 1. So that's your unique solution. Is that clear? Okay. Of course, you're not going to do reduced of echelon form by hand, right? Go to MATLAB, say RREF, bomb. Go to Python, say RREF, bomb. Okay, so one line of code. So, but the reasoning, when you do reduced of echelon form, it's going to tell you exactly what the solution is. All right, but we don't always have solutions, right? For example, here, think about those 2 lines. X plus y is equal to 3. Okay, that's this solid line. And then we have 2x plus 2y is equal to 5. Do they intersect at all? That means there is no solution, right? So how do I do that? I just, again, create augmented matrix, 1, 1, 2, 2, 3, 5, and do reduced of echelon form. I go, sorry, too much. And this is my reduced of echelon form. You see that right there? There's a problem here because I was not able to convert it to 1, 0, 0, 1. And that means here, when I look at the first one, this says x plus y is equal to 0. And then here, it says 0 is equal to 1. Can 0 be equal to 1? No, that means there's no solution. Okay? So I go here. The first one says x plus y is equal to 0. This says 0 is equal to 1. Since it cannot happen, we say no solution. Are you with me? All right, let's go. Another example. Oops. Oh, this was this example. Sorry. Okay. And here it is. Now, when I look at this, I'm going to create augmented matrix. These, as you see, these are all ones, and then 1, 2, 3. And then I do reduce through echelon form again. Boom, I ended up with this one. What does this tell you? X plus y plus z is equal to 0. 0 is equal to 1, and 0 is equal to 0. The first one, I'm okay with it, right? X plus y plus z is 0 is fine. 0 is equal to 0, but the middle one is not. So that means we don't have a solution. Okay? And well, sometimes we have many solutions. For example, look at this. X plus y is equal to 3. That's the solid line. I multiply everything by 2. That's exactly the same line, right? Two lines intersect at infinitely many points. Do you agree? So sometimes we have many solutions. So this is what it is. I'm going to create the augmented matrix. Then I'm going to do reduce through echelon form. All right. Now I ended up with this. Well, x plus y is equal to 3. Do you agree? No problem there. And 0 is equal to 0, right? No problem there too. So in this case, we have many solutions because I can have many x and y that satisfies this. For example, 1, 2. 1 plus 2 is 3. Negative 5 plus 8 is also 3, right? So I have many, many solutions. And typically what I do here, I create a free variable. I call it s. For example, y is equal to s. If y is s, then x is equal to 3 minus s, right? And then I can go from here and I can say x, y are all vectors, 3, 0 plus s times negative 1. So that is a set of solutions for x and y. Is that clear? Any questions so far? Okay. So let's have another example. And this is a little bit more complex. I created reduced through echelon form right here. Okay, so this is the reduced through echelon form here, as you see. What does it tell? It says x is equal to 5. Y plus z is equal to negative 2, and 0 is equal to 0, right? So basically, that's exactly what I say. X is equal to 5. Y plus z is equal to negative 2. And then again, there are many, many solutions that you can find. In such cases, we know x is for sure 5. We cannot play with it, right? But then y plus z is equal to negative 2. Then I'm going to make z as a free variable and then represent y in terms of that free variable. And this is exactly what I do. X is 5. And then I say, let's say z is s, then y is negative 2, negative s, and then x is 5. That's the solution. So everybody's okay with that? So to sum up, we may have a single solution, we may have no solution, or we may have multiple solutions. All you have to do is reduce through echelon form and then look at it. Is that clear? Okay, so now let's talk about more stuff. What is a vector space? Don't be scared when it says space. Space is nothing but a set. Okay? But that's a special set. A set consists of objects. So a vector space consists of objects. But those objects can be added together or can be multiplied by a number. Okay? So not any objects. Objects that can be added together or can be multiplied by a number. We call scalars. Okay? But scalars can be real numbers. If scalars are real numbers, then you call real vector space. If scalars are complex numbers, we call it complex vector space. Okay? In general, if you are familiar with mathematics, those scalars can be any field. Real numbers and complex numbers are fields in mathematics. So it can be any field, but I'm not going to get into details. So real vector space, complex vector space is nothing but a set of objects that can be added together and multiplied. But they have to satisfy certain axioms. It's not just any set of objects. And I listed those axioms right here. See, I'm not going to go each one, but basically a set V is called a vector space over field F. F can be real numbers or complex numbers. In our case, data science, real numbers, right? So a vector space is a set V is a vector space over real numbers when those axioms are satisfied. For example, if you get two vectors in the vector space, if you add them up, the new vector is going to be also in the vector space. You understand? And then when you have three vectors, doesn't matter where you add them up. That's associativity. Or the addition, the first plus second one is equal to second plus first one. Simple stuff. And then there is an identity element that you can add it to any vector and it will not change that vector. And there's also an inverse element. When you add it, you're going to get the identity element. You understand? So that is object addition. Also, you have 5 axioms for scalar multiplication. When you multiply a vector by a scalar, you end up with another vector in the same vector space. Okay? And then we have those 4 more. So a vector space is nothing but a set. All right. So for every vector space, we are talking only finite dimensional vector spaces here, but there are also infinite dimensional vector spaces, which is out of scope. But for every vector space, there is always a basis. Okay? Basically, a basis, you can find certain number of vectors, okay, certain set of vectors in the space, and any other vector can be represented as linear combination of those vectors. Does it make sense? For example, in R3, you can find 3 vectors. Any vector in R3 can be represented as linear combination of those 3 vectors. Then that's a basis. Basis doesn't have to be unique. You can have 3 vectors as a basis. You can find another 3 vectors, for example. Okay? So basically, now we're going to learn how we can find it. And the number of elements in the basis determines the dimension of the space. Why R3 is 3-dimensional? Why do you think R3 is 3-dimensional? Because there are 3 basis vectors that you can find. Why R2 is 2-dimensional? Because there are only 2 basis vectors. Why is a line 1-dimensional? Because if you get a vector, you multiply it with, and you can get any other point in the line, right? So because there's only single basis vector for there is one vector that can act as a basis for a line. So here it is, the first one, and everybody's familiar with that, I'm supposing. This is R3. You have E1, E2, E3. And if you have those 3 vectors, and if you get any other vector in R3, can I write it as linear combination of E1, E2, E3? So that means E1, E2, E3 is a basis for, well, there are little tricks that I'm going to talk about. But basically, this vector P can be written as linear combination of those 3. And there's a little bit more. I'll talk about span. But these 3 are the basis vectors. They don't have to be only those 3, by the way. So some of the vector spaces, very well known. Rn is a vector space, and each point in Rn is written as n tuple, right? And then when you have a vector in Rn, this is the length of the vector. Do you agree? I mean, this Euclidean length of the vector. So vector in R3 has a length concept, right? In general vector spaces, we have similar thing we call norm. We talk about norm of a vector. Norm is a concept of length of the vector or the object in the vector space. Okay? Yep. For general vector spaces, we need a concept that corresponds to the length in Rn. We use norm instead of length. So there are certain vector spaces that have norm, the length of the object. So a norm is nothing but a function that takes an object in the vector space and map it to a real number, because length is a number, right? So that takes a vector in the space and map it to a real number. But it needs to satisfy three properties. Not all functions can be norm. It needs to satisfy those three properties. First of all, length cannot be non-negative, or cannot be negative. It needs to be non-negative, right? So, and then this is called triangle inequality. Basically, I have another slide for this. For example, when you have two vectors, you add them up. This is the addition of two vectors. The length of x plus y is less than or equal to length of x plus length of y. Basically, there are three things that needs to be satisfied by that function to be a norm. And the most commonly known norm is our L2 norm, which is Euclidean norm, and which is, everybody's familiar with this, right? And get the square of each element in the tuple and finally get the square root. But this is not the only norm. We have, in general, p norms. Okay? So get familiar in data science when you say, hey, L2 norm is Euclidean norm, basically. But there are p norm, LP norms. And here, if it is p norm, then instead of 2, you have power p. And instead of square root of 2, you have square root of what? P. And here, for example, if p is 1, this is called L1 norm. And in L1 norm, if you put 1 here, that means the sum of the absolute values of each element. Okay? For example, when I say C is equal to, let's say that the norm is C, L1 norm, that is this prism here, right there. Any point here, any point in this surface has exactly the same norm. And if for R2, that is a sphere, as you see here, any point on the sphere has the same R2. This is the square, sorry. I forgot the square root right there. Okay. And then we also have an infinity norm. So infinity norm, you take the maximum element, maximum of the absolute values of each element in the tuple. So L2 norm is very commonly used. There are reasons that we have L1 norm, also and infinity norms. There are different cases. For example, Gaussian noise. Have you worked with noises in your research? We always had Gaussian noise, right? Well, Gaussian noise, if you have a Gaussian noise and if you want to eliminate it, you typically work with L2 norm space. But if you have Laplacian noise, which is a very different noise, you typically work with L1 space. And these are like things that you may get familiar in time. So what's a subspace? Well, a subspace is, a space is a set, right? So what do you think a subspace is? A subset. All right, that's basically it. So when you have a space V, a subspace W is a subset of the set V. And instead of checking all those 10 axioms, you only need to check 2 things. Okay, so a subset W is a subspace if for any scalars alpha and beta and any objects V and W, this combination is also in the subspace. That's basically what does it mean? It's extremely simple. Look at this. We are in R3. R3 is V, right? The whole space, R3 is V. Now, think about this line. Think about all the points in this line. Is that a subset of entire space? This line lives in R3, right? That means that's a subset. Do you agree? And if you take any point, let's say this point and this point, and if you multiply this point, any scalar, are you still on the line? If you multiply this one with any scalar, are you still on the line? And if you add them up, are you still on the line? That means a line is a subspace of R3. Okay? It is simply one-dimensional subspace of R3. But think about this plane. Think any point on the plane. If you multiply by a scalar, are you still on the plane? If you take another point and multiply by a scalar, you're still on the plane, right? If you add them up, are you still on the plane? Yes, so that means this plane that passes through origin is a subspace of R3. Do you agree? So that's basically what it is. So we'll talk about 3 things. in order for a set of vectors to be a basis for a space, they need to be independent and they need to span the entire space. So what does it mean? Okay, so I'm going to explain what independence mean and what does spanning mean, because set of vectors are a basis if they are linearly independent and if they span the space. So what is the linear independence? Think about those two vectors. Are they linearly independent to you? The second one is twice as the first one, right? So they are not linearly independent, because knowing the first one, you can always determine the second one, right? So that's the idea. So, and in order to determine if they are linearly independent or not, first create the matrix 1, 3, 2, 6 and find the reduced rough echelon form. Once you find the reduced rough echelon form, it's gonna be 1, 2, 0, 0. See, we have two vectors, but there is only one here. You see that? There is no one here. So that means there's only one pivot. If there is only one pivot, those two vectors cannot be linearly independent. Is that clear? And in fact, by looking at this reduced rough echelon form, you see this is 2. That means second vector is twice as the first vector. Really, W is like twice V, right? So here it is. And that means I can say W minus 2V is equal to 0. So they are not linearly independent. And here's another example. How about this time? I have 1, 3, 2, 7. I create the reduced rough echelon. I find the reduced rough echelon form. Do you see 1, 1? I have two pivots. That means they are linearly independent. Does it make sense? Okay. And really, I mean, 2, 7 is not a multiple of 1, 3, right? So they are linearly independent. How about this 3 vectors? So what you do, you put them in a matrix, and then you find the reduced rough echelon form. Do you see this is 1, 2, but we only have 2 pivots, right? We don't have 3 pivots because this one is 0. 3 vectors, 2 pivots. That means they are not linearly independent. And in fact, look at here. We have 1, right? That means the third vector, V3, is 1 time V1 plus 1 time V2. Here you go. By looking at this, I say V3 is V1 plus V2. Okay? And here is another example. I'm going to go a little fast. 3 vectors. I find the reduced rough echelon form. This time it is like that. Since we have only 2 pivots, that means they are not linearly independent. And when you look at this here, 1 and 2, what does that mean? This vector is 1 time V1 plus 2 times V2. Are you with me so far? Yeah, very good. And then I'm going to go a little fast. This time, when I find the reduced rough echelon form, I have 3 pivots, right? That means they are linearly independent. And 2 vectors, and I find the reduced rough echelon form, and I have 2 pivots, right? I have 2 vectors, 2 pivots, that means they are linearly independent. Okay. Well, pay attention. If we are in R2, okay, and if you have 3 vectors in R2, they are not, 3 vectors in R2 will be linearly independent unless they, they are like coinciding with each other as a line. But I'll skip this. Span, let's go to span. Span means, so linear independence means what? You can represent the linear combination of those vectors. You cannot have linear combination of those vectors unless all coefficients are 0. But here, span, think about this, 0, 1, 0, 0, 1. With these 2 vectors, I can represent any vector in R2. Do you agree? Like 3, 5. 3 times E1 plus 5 times E2, right? That means E1 and E2 span R2. Okay? And here, 1, 3, 2, 7. How do we find if they can span or not? So I'm going to find the reduced rough echelon form again. You see how strong the reduced rough echelon form is. And then I'm going to look. I have pivot 1, pivot 2. So I have 2 vectors and 2 pivots. That means they span R2. for sure. And here, again, I find the reduced of echelon form. And look here. I have 3 vectors, but what is the dimension of the vectors? 2, right? So each vector is 2-dimensional. Each vector is in R2. Do you agree? And then when I do reduced of echelon form, I have 2 pivots. I have 2 pivots, 3 vectors. They cannot be linearly independent. But I have 2 pivots, and I am in R2. That means they span R2. Do you understand? So if I have those 3 vectors, I can write any other vector in R2 as linear combination of those 3 vectors. Okay. Another example. Think about this. I do reduced of echelon form. I have only 1 pivot, right? 1 pivot and 1 pivot, and I have 3 vectors. That means they are not linearly independent. And 1 pivot, and I am in R2. That means they don't span R2. Okay? So reduced of echelon form is so important. If a set of vectors are linearly independent and they span the space, they are bases for the space. Very easy. Think about this too. V1 and V2, they are linearly independent and they span R2. So what does that mean? They are a basis for R2. Think about this. 1, 3, 2, 7. They are linearly independent as we showed before, and they span R3, so that means they're a basis for R3. How about this two, those 3? By looking only 2 vectors in R3 cannot be a basis. Minimum of 3 vectors are needed, right? But minimum of 3 vectors does not guarantee that they will be the basis. So they have to span as well. So here, V1 and V2 are linearly independent, but they don't span R3, so they are not a basis for R3. Okay, another one. We have 3 vectors. They are linearly independent, and they span R3. We did show with the reduced of echelon form. Since they are linearly independent, they span R3, we can say that that's a basis for R3. Are you with me? Am I going too fast? And we are going to share those lecture notes, don't worry, so that you can have access. And another one, now we have 3 vectors. They are linearly independent, but they don't span R3, so they are not a basis for R3. Okay? Now, those 3 vectors, they are not linearly independent, but they span R2, but since they are not linearly independent, they are not a basis for R3. Why aren't they linearly independent? Look at here. 1, 3, twice. If you multiply V1 by 2, you get V2. If you multiply it by, it's supposed to be 9, I guess, right? 3, 9. Yeah, it's supposed to be 3, 9. So then make the correction, okay? So they are actually linearly independent. Well, no, they are not linearly independent still. Oh, yeah. They are still not linearly independent, of course, because this is multiple of this, right? So this is correct, no error. But that's not a basis for R2. Here, they are not linearly independent. They don't span R2. That's not a basis for R2. All right, here is an example for you. When 4 vectors are given to you, how do you determine if they are linearly independent? What do I do? Reduced of echelon form, right? And how do I know if they span R4? Still reduced of echelon form, right? So reduced of echelon form will tell me everything about this. So, and how do I know if they form a basis? If they are linearly independent and if they span, that's a basis. So let's go ahead and do it. Here, I'm going to find the reduced of echelon form. I did. How many pivots do I have? 1, 2, 3, right? How many vectors do I have? 4. So are they linearly independent? Okay, so how many pivots do I have? 1, 2, 3. What is the dimension that I am working on? 4 dimensions. So do they span? Yeah. Exactly. So are they a basis? No. Okay. All right. But which one of those are, okay, out of 4, since I have 3 pivots, okay, What is the dependencies? Like, look at this one. This says -1. That means this guy, you see here, this guy can be written as linear combination of -1 times the first one plus this guy 1 times second one. You see that? Okay. So that's all I have as the first part. I'm going to go to second part. Do you have any questions here? How many minutes did I take for this? Okay. So second one is going to be shorter. All right. Okay. Give me 1 second. This part is shorter and okay. Yes. All right. So anybody has any questions? Ask me a question from the first lecture. Do you have some prizes for good questions? Maybe? Okay. This is what? This is R3. This is space. Okay? And you are an object of that space. You are a vector.
Like
No.
I have some points like 2, 3, something like that.
Well, it doesn't make exactly correspondence, but this is, we live in R3, basically, okay? And this guy is a vector in R3, not you. You are curved. Okay? Ask me a good question. So, do you feel comfortable now what a basis is? What linear independence? What span, space, a subspace, at least in the short amount of time, right? So now let's talk about some matrix operations. Okay, I need to do again. So we are going to talk about some very fundamental matrices, matrix inverse, matrix rank. Rank is your best friend. Okay? Rank is so important. Maybe you heard about it in linear algebra, but you don't know why it is important. But rank is very important. You will understand why. And then we'll talk about column space, and we'll talk about projections a little bit, if this works again. Here you go. Yep, we said a matrix is nothing but a rectangular array or two-dimensional array, right? And matrix addition is, of course, obvious when you have two matrices of the same dimension. For example, this is a matrix of 3 by 4. Why? We have 3 rows and 4 columns, right? And there's another matrix. This is also 3 by 4. Then you can add them up. When you add them up, you add individual elements, and you end up with another matrix. And the matrix multiplication, well, when you are multiplying two matrices, you have to pay attention to the dimensions, okay? Not every two matrix can be multiplied. For example, here, let's say that you have a matrix A, m rows and columns. That means m by n matrix, right? And then you have another matrix, and this time n rows, r columns. This is n by r matrix, right? Then you can multiply them. Why? Because you see n here. The number of columns of A is the same as the number of rows of B, right? Then you can multiply them. Otherwise, you cannot multiply. And the dimension of the multiply, the product of those two matrices will be m by r. Skip n, it's going to be, what is going on with? And then this will be m by r. Are you with me? And that's very, very simple stuff to do. Think about those two matrices. And A is 3 by 2. This is 2 by 4, right? So 2 is common, so you can multiply them. And how do you multiply them? By the way, when you multiply 3 by 2, 2 by 4, you're going to end up with 3 by 4 matrix, right? And what you do, you first take the first row of A and first column of B and multiply them. 1 times 1 plus 1 times 3, 1 times 3, which is 4. You see that? And then you take the second row and 1 times 2 plus 3 times 3, which is 11. You see that? And you add there and get the third one. Again, 1 times 3 plus 3 times 4, 15. And then you go second one, third one, and so on. Everybody's okay with that? Matrix multiplication. Matrix addition, the same dimensions. Multiplication, number of rows must match the number of columns of the first one must match the number of rows of the second one. So why is it important? Well, this is our set of equations, right? Sorry, I know this is not showing here, but of course there's a square bracket here. I'm assuming you understand that, right? Okay. So, and then I can write this one 2, 1, 1, 1, and then xy. If I multiply xy with this matrix A, this is AX is equal to B. This is B, by the way, okay? So you can write, you converted this problem into a matrix multiplication problem. AX is equal to B. And or here, for example, this is your set of equations. This is your matrix A. This is X, vector X, and this is B. AX is equal to B. So that's the problem that you converted to. What's transpose? And you invert rows and columns. So the first row becomes the first column. Second row becomes the second column, and so on. So here, and look here, this is the first row. It became the first column. Second row, second column, and so on. So if original matrix is 3 by 4, transpose is what? 4 by 3, right? If A m by n, then you have n by m. What is the transpose of transpose? Itself, right? Okay. So basically, when you have two matrices A and B, you multiply, you get this one. And then take the transpose. This is your first column. It becomes first row, right? So A, B, you multiply them and you take the transpose. Instead of that, let's go this way. First, let's take the transpose of A, transpose of B. Let's multiply them, B transpose, A transpose. You see they are the same exactly. So what does it tell us? The transpose of product of two matrices is the transpose of the second one multiplied the transpose of the first one. Okay? All right. Of course, for addition, when you have two matrices, you add them up, you take the transpose, or you take the transposes first, add them up, they're exactly the same. In other words, for transpose, this is what you have. A plus B transpose equal to A transpose B transpose. This is very important. When you have two vectors, inner product. Inner product, I will show later, is a measure of angle between two vectors. Okay? You have one vector, you have another vector. What is the angle between them? If the inner product is 0, for example, that means they are perpendicular to each other. Do you understand? So norm was a concept of length. Inner product is the concept of angle between two vectors. Okay? And this is how you do it. V1 dot V2. That means V1 transpose times V2. For example, this is V1. What is the V1 transpose? A, B, C. And then we have V2, X, Y, Z. And if you multiply them, you get what? A times X plus B times Y plus C. So that is a number. You see that? Inner product, vector inner product, is the inner product of two vectors is a number. If that number is 0, that means those two vectors are perpendicular. If that number is 1, they are heading in the same direction. Okay? Or they're exactly the same, you know, and the length is 1, what we'll talk about. If they are negative, that means they're heading on the opposite directions, right? And this is another notation. You can have triangular brackets for this. Identity matrix. Well, a matrix with all diagonal elements are 1 is an identity matrix. For example, this is an identity matrix. This is also an identity matrix, right? Okay. Matrix inverse. Well, matrix inverse is defined only for square matrices. You cannot have an inverse of a matrix unless that's a square matrix. What does square matrix mean? It means the same column, the same number of columns and rows. Okay? So here, this is n by n. Then you can define the inverse. The inverse means if you have a matrix A, and if you multiply by inverse on the right side or on the left side, you get an identity matrix. Okay? Inverse of a matrix means multiply it by the inverse, you are going to get an identity, whether from left or from right. So how do we find it? I'm going to go a little fast here. There is a concept called Gauss-Jordan elimination. Of course, you're not going to go and do it with Gauss-Jordan manually, right? It is just one line of code, inverse A, in Python or MATLAB or any tool. But I just want you to understand, in order to find the inverse of this, you create an augmented matrix like this. You add your matrix and 1, 0, 0, 1. Again, do row echelon, reduced row echelon form. So somehow convert with the row operations the first part to 1, 0, 0, 1. And this is your inverse right there. You see that? Reduced row echelon form is so strong. So here I started with my original matrix. I augmented with 1, 0, 0, 1 with an identity matrix. I did row operations, and I converted the first one to an identity matrix, and this part is the inverse of the matrix. For example, here, I start with this, I do this, put the identity matrix, do a lot of row operations, and finally convert it to this format. This is identity, and this is your inverse. Okay? So if this is the matrix, this is the inverse of that matrix. Does it make sense? I mean, at least procedurally, right? Okay. So what is the rank of a matrix? This is very important. Let's say that you have two vectors, 1, 2, 3, 2, 4, 6. What is special about those two? 1, 2, 3, 2, 4, 6. The second one is twice as the first one, right? So how about if you have another one? 3, 6, 9. 3 times, right? So I have 3 vectors. But do I know that they are multiple of each other? In the computer, when you store those 3 vectors, do you want to store them as 3 vectors? Or maybe 1 vector and 2 numbers? 1 vector and 2 numbers, because the second one is a multiple of 2, other one is a multiple of 3, right? So if you have like so many such vectors, you don't want to store each vector, right? Because it doesn't make much sense. Because second vector is a multiple of the first one, third one is a multiple of the first one, and so on, right? If the rank of a matrix is 1, no matter how many elements, how many columns you have in that matrix, that means each one of those columns is multiple of only 1 column. Do you understand? So that means there's only 1 independent vector. The rest all depend on the first vector. So rank 1 means only 1 vector needs to be stored, really. Let's say that you have a matrix of 40,000 by 10,000, right? Huge matrix. But the rank is 5. Even though you have 10,000 columns, each one of those 10,000 columns is nothing but combination of 5 vectors. Do you understand? So rank determines the dimension of subspace. In other words, instead of working in 40,000 dimensional space, if rank is 5, you need to work in 5-dimensional space. Because all you need is 5 vectors. Do you see how important rank is? Okay? So it is the number of independent columns or rows. For example, here, 1, 2, 3, 2, 4, 6. And even though I have 4 columns, there's only 1, right? How do I find it? Reduced row echelon form. How simple it is, right? This reduced row echelon form is like magic. So simple. So I do reduced row echelon form. How many pivots do I have? That means rank is 1. Okay? And of course, in MATLAB, for example, I put here, let's say that I have this matrix A. Are you familiar with MATLAB? Anybody is familiar with MATLAB? You don't have to. This is just common sense. When you look at the screen, that's so simple, okay? Look, here we have a matrix A. 1, 2, 3, 4, column 2, 4, 6. This is my matrix A, okay? And then I do what? Reduced rough echelon form of A. This is the reduced rough echelon form of A. And then by looking at this, I can say there's only one pivot, rank must be 1. Or I can directly apply rank A command of MATLAB, and here it is. If you're familiar with Python, that's even easier, right? In Python, this is your matrix. You do reduced rough echelon form, and that's here, right there. Or you can just say A.rank. That's going to give the rank. Right. You feel comfortable so far? Okay. Here you go. What is the rank of this matrix? By inspection, I can say that the rank is 2. Because look, this one, like look at this row here. Oh, by the way, you can do the same thing from the rows. Doesn't have to be just columns, okay? And here, by looking at this, look, or let's look at this column and this column. Look at that. This column is 3 times the first column and 6 times the second column, right? And this one, 4 times the first column, 8 times the second column, 100 times the first column, and 300 times the second column. Oh, we have 1 here. Okay. So, and then, but it cannot be just those 2 columns, right? For the third one. So by inspection, 1, 2, we have 3 pivots actually, right? So the rank is 3. I initially, yeah, there is probably this was 0 in my initial thinking, okay? See, while I was explaining, I was thinking the same thing. But yeah, assume this is 0, then this is rank 2, right? I'll make that correction. All right. So matrix rank cannot be bigger than, for example, if you have a matrix m by n, rank cannot be more than the number of columns or number of rows. For a square matrix, for example, if you have a square matrix with the same number of rows and columns, rank can be maximum of what? N. Okay? If you have 10,000 columns, rank cannot be bigger than 10,000, right? Yeah. And if the rank of the matrix is the size of the square matrix, we call it full rank. Let's say that you have 10 by 10 matrix, and the rank is what? 10. That's full rank. That means each column is linearly independent. Columns are completely linearly independent. 10 of those columns are linearly independent. Okay? And let's talk about the inverse of a matrix. When you have a matrix A, look at here. What is the rank of this matrix by inspection? Is it full rank? No, then you cannot have the inverse of this matrix. Okay? In order to have an inverse for matrices, you have to have full rank. Okay, how about this one? What is the rank of this matrix? 3. So you can define the inverse for this matrix. Okay. So matrix inverse is important. For example, here, when I say AX is equal to B, what if I multiply both sides by the inverse of A? A inverse AX is equal to A inverse B, right? What is A inverse times A inverse? That's the identity matrix. So that means the solution is A inverse times B. See that? And then all you need to do is take the inverse of this matrix, and then XY becomes the inverse of this matrix multiplied by B, 3, 1. And you can also find that this is 2 and negative 1. Okay? So you can do multiple ways to find a solution to a set of linear equations. And if it is invertible matrix, and if it is square matrix, invertible matrix, you can do this. The inverse of inverses itself, I'm going to skip those. These are not very, very important. Oh, this is important. Matrix multiplication is not commutative, okay? When you have AB, and when you look at BA, they are 2 different matrices. So AB is not necessarily equal to BA. What is sparse matrix? Sparse matrices are very important in data science because many times you end up with sparse matrix. Sparse means many of the elements are 0, simply. For example, A is a sparse, B is a sparse matrix. and square matrix, equal number of rows and columns. Symmetric matrix, look at the diagonals, and 5, 5, -3, -3, 2, 2, right? That is symmetric matrix. Skew symmetric matrix, again, the diagonals are 0, and then those are like opposite signs. -5, 5, -3, 3, 1, -2, -1. So that's skew symmetric matrix. Triangular matrices are important. So when you have the diagonal, either lower diagonal or upper diagonal will be what? Zeros. So that's a triangular matrix. Diagonal matrix, all diagonal elements are non-zero, but the rest of the elements are 0. Okay. Identity matrix, we already talked about it. Null matrix is if all elements are 0. And okay, let's think about this. A and B. I multiply A and B, and I end up with 0, 0. See, two non-zero matrices, when you multiply them, you may end up with 0. That doesn't mean that one of them is null. Determinant, you heard about determinant. I'm not going to tell how you are going to find it, but that's a scalar. So basically, a determinant of 2 by 2 matrix, we use pipes like this, multiply those two diagonals, and then subtract the product of those two diagonals. Okay, so that's basically a number. And in MATLAB, it is just DET comment, and also it is DET comment. Why is it important? For diagonal matrices, for example, when you have a diagonal matrix like this, 2, 5, 6, you see that? That's a triangular matrix, sorry. When you have a triangular matrix, the determinant is the product of the diagonal elements. Okay? If it is not full rank, determinant is always 0. If you have a matrix whose determinant is 0, you can say that is not full rank immediately. You don't have to do rank analysis. Rank cannot be full rank. This is what it is. Think about this matrix A. I do reduced of echelon form. We have 2 pivots. That means the rank is 2. Rank is not full. And then if I find the determinant of this, I will end up with 0. Okay, let's skip this one. This is not very crucial. Okay, this is important. So let's remember subspaces. R3 is our vector space. And then we have a line that's a subspace. And then plane is a subspace. I already explained this, right? When you have 2 points in the line, if you add them up, you're still on the line. And you have 2 points on the plane, if you add them up, you're still on the plane. Union of subspaces. Think about this. This is one subspace line. This is another subspace plane, right? Union means what? You take 1 point from one subspace, you take another point from another subspace, you add them up. But in this case, if I take a point Z2 in the line, and if I take a point Z1 on the plane, if I add them up, is it going to be on the line? Is it going to be on the plane? No, right? I end up with a point which is not on the line, not on the plane. So that means union of 2 subspaces may not be a subspace. Does it make sense? You have a line, you have a plane, you take the union of them, but the union may not be a subspace because the point Z2 plus Z1 is not on the line, not on the plane, so it's not on the union of those 2 subspaces. Intersection of 2 subspaces, basically, think about this. This is your subspace. This is another subspace. What does intersection means? All the points that are both on first subspace and also on the second subspace, right? What do you think it is? If you have this, what are all the points that are on the blue surface and also on the orange surface? Can somebody tell me? That's the line, right? Exactly. Very good. So this is here. And this line is in the intersection of those 2 subspaces. So intersection of 2 subspaces is another subspace. All right. This is the last thing that I'm going to explain. Column space. And column space is important. What does column space mean? Column space of matrix A is all linear combination of the columns of A. What does that mean? So We'll think about the column 1. Is it in R4? Column 2 is in R4. Column 3 is in R4, right? So all those linear combinations of those 3 will be in R4. In other words, row space or the column space is or range, column and space and range space are exactly the same thing. Range space of A is a subset of R4. Do you agree? Because all linear combinations are in R4. Okay. So why is it important? Look at here. This is AX is equal to B. For this to have a solution, B1, B2, B3, B4 must be linear combinations of this first vector, second vector, and third vector. Why? I repeat, for this to have a solution, vector B must be linear combination of those 3 columns. Why? Why? Because this means x1, B1 means x1 plus x2 plus 2x3, right? B2 means x1 plus 2x2 plus 3x3, right? And B3 is 2x1 plus 3x2 plus 5x3. And B4 is 2x1, 4x2, 6x3, right? So that must be B1, B2, B3, B4 somehow must be linear combination of those, the elements of the columns of the matrix. So in order for AX is equal to B as a solution, if B is in the column space of matrix A. So how do you find it? Again, reducer of echelon form. This is A, okay? And I find the reducer of echelon form. You see there are 2 pivots, and that means only the first 2 are linearly independent, and I will go to the back. I will say that's first column and second column are linearly independent. The third column is linear combination of those 2. In other words, my range space or column space is spanned by those 2 column vectors. Does it make sense? I know this might be confusing. What I did, I find the reducer of echelon form, and I go back to the original columns. I say the first 2 original columns are linearly independent, and they span R3, so they are a basis for column space of A. I'm going to stop at this point. And then let's give a break, and then Tim, you come back, and then we'll continue.